Inverse variation is yet another way to model the relationship between two quantities. It is actually the last way we will model the relationship between two quantities in this particular class. It comes from section 4.4 in your textbook, and in this section we will write and solve equations for scenarios that have inversely varying relationships. So we'll look at some data with a brand new relationship. I do have a couple of recalls. First, direct variation. We've seen that in the past. Direct variation meant the relationship between the two quantities was proportional. Okay, and when that happened, we could make a linear model for it, and that linear model, so let's write that down to remember it. So direct variation has the linear model y equals kx, or if you prefer y equals mx or constant change x, right, with 0 as its initial value. So I remember vaguely we did some examples where we did money exchanges, and those are direct variations. They are definitely proportional. How much you get in the other currency is proportional to how much you have. And if you have $0, then you will get 0 yen, or $0 exchanges for 0 yen, exchanges for 0 pesos, exchanges for 0 rubles. So they definitely have a linear model where the initial value is 0, and they're proportional. So when we're thinking about financial currency exchanges, that is definitely an example of this. We didn't cover it, but one example that pops up into my life is actually like how many hours you spend cooking a turkey. Anyway, based on how many pounds it is, and how many pounds of turkey you get based on how many people are eating. Whatever. One of those moments where I didn't realize it was going to pop up, but it did. Okay, in example 1, find the pattern, fill in the table, graph the data. Okay, so here we have 1 corresponding to 1, a half corresponding to 2, a third corresponding to 3, a quarter corresponding to 4. Okay, then I see we're dividing by the amount. We are partitioning. We're making fractions out of X number of fractions here. Okay, so here we go. I'm just going to make these a little bolder and note that it might be good if we count by every other. So let's go 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left, and 1, 2, 3, 4 going up, and 1, 2, 3, 4 below. Got it. Let's plot these points. We have 1 to the right, 1 up, 2 to the right, a half up, 3 a third is just below, 4 and a quarter. Got it. Okay, so I see it trailing off here, getting closer. I'm not sure what's happening anywhere else, but I see it's looking a little bit like an exponential. Write an equation to describe this relationship? Oh, sure. Well, I just put that x in the denominator and turned it into a fraction. So if I had 2, I took a whole and divided it by 2 to get a half. So 1 portion. What happens when you try to input 0 into this equation? Oh, right. We get an error. Why? We can't divide by 0. No division by 0. Okay, so what that means to me is if x can't be 0, this is weird. So normally with an exponential, we would cross the y-axis at some initial value and then keep going up. This would look like a decay. But it's saying we can't even put in 0. So, my curiosity says, what's happening there? So let's actually figure out what's happening as x gets closer to 0. Okay, use your equation to find the y values for the following input. Okay, so remembering that our equation is 1 divided by whatever x is, let's put in 1/2. This is awkward, so I'm going to rewrite it as 1 being divided by 1/2. And this is saying how many halves are there in 1? Well, there are 2. I think of this and I think, okay, if this were a 10 and this were a 2, 10 divided by 2, how many sets of 2 are there in 10? There are 5. How many sets of 1/2 are there in 1 whole? There are 2 of those. So just to count it, looking at it like that, because then this would be how many thirds are in a whole? 3. How many quarters in a whole? 4. How many fifths in a whole? 5. Oh, okay. And then these are just negative style. So -2, -3, -4, -5. Ooh, 1 divided by -1, -1. So with x being 2, this would be -1/2. Divide it into thirds again. Take the opposite, -1/3, -1/4, and -1/5. Now go back to your graph and edit it to complete the picture. Okay, to find out what is happening. Let's find out what's happening there because we couldn't divide by 0. Let's plot these points. So at 1/2, it's at 2. And at a quarter to the right, it's 4 up. So a quarter to the right, 4 way up here. Whoa, I see. So it's actually going up and up and up. So it's actually not hitting the y-axis, it's just going really high. Okay. And this is not crossing the x-axis, it's just approaching it. So it's becoming more fractional and not going below. Huh, very interesting. That's definitely different than the exponential graph. And let's see what's happening on the left side. So if we're at left 1/2, we're down 2. Whoops, really missed my mark there. Okay. Got it. And let's see, left 1/4 down 4. So left 1/4 down 4. Left 1 down 1. Left 1 down 1. Left 2 down 1/2. Left 2 down 1/2. Got it. Left 4 down 1/4. Okay, so I see a similar thing happening over here that happened up here to the right and above. So let's connect those. Oh, wow, that really is a new model compared to what we've seen before. It's almost like they have they have these moments where they're getting closer to things, and it almost feels like they're repulsive to each other too, like they're repelling each other. So definitely a new relationship. Wonder how it's used. So a couple of remarks about this new relationship. Okay, so it is not linear. It is definitely not quadratic or exponential either. So this relationship definitely is a brand new model, a brand new pattern, and the image is certainly different. Okay, this pattern has a model that involves a relationship of division by x, and those also did not involve that. So this so here we had y equals 1 over x. So this division by x really created a brand new image and pattern for some data. And then another remarkable thing about this is that I want to bring you back to the direct variation. So direct variation had this relationship of y equals k times x, and this new one this model isn't times x, it's divide by x. And in this particular case, the k was 1. But direct variation said, we're going to model this with y equals kx. And this model had y equals 1 over x, or k over x. So you could see how we would have a direct variation and an inverse variation. One is multiply by x, the other, so scale up, scale down, basically. All right, so let's write down what the definition of inverse variation function is. So if y equals k over x, or k divided by x, for some non-constant k, non-zero, silly Abby, non-zero constant So if y equals k over x for some non-zero constant number k, then we say y varies inversely with x. Okay, but I'm going to write more about this because I remember us talking about direct variation as being a proportion. And here it is also a proportion. So another way to say this is that y is inversely proportional to x. So So another way to describe this relationship is by saying y is inversely proportional to x. So it's still proportional, I mean, but now we're kind of just differentiating between direct variation and inverse variation, okay? Yep, skill up, skill down kind of business when it comes to these. So in the next video, let's take a peek at some of these, yes? Let's use and differentiate between direct variation and inverse variation.